Hello, I welcome you to the channel Microwave Testing. We are addressing the non-destructive testing of parts for defects, especially for those defects which are under the surface of the parts and cannot be seen directly. And we do not use standard methods of NDT like ultrasonic testing or X-ray testing, but we use microwave testing. This method is especially useful to investigate parts made from glass fiber reinforced plastic, GFRP, or other non-conducting materials. If you are interested in the basics of microwave testing, then you are in this right video. Regarding microwave testing, I had been asked how the shape of an indication of a defect arises. Well, we will come back to that question in the next video of this series. Today we will see the effect when a plate moves back and forth in front of a microwave test head. Here we see the test setup, in the background the laptop operating as an oscilloscope. This is the test head with the antenna. On the right hand side we have the plate with a hand stick to move it. Now we begin to move it, and we have the insert which describes enlarged what there is to be seen on the screen. Well, especially we can recognize that when moving the plate backwards, we have a spiral. That means a circle of the point, and the amplitude becomes smaller. Now we want to understand this spiral behavior. Well, we have a transmitter with an antenna, say in this case with a frequency of 24 gigahertz. This is irradiating a wave, an electromagnetic wave. Well, a wave is characterized by its wavelength. That means the distance between two equal points. For example, these minima. In this case, the wavelength is 12 millimeter. Well, lengths are sometimes also given not in millimeter but in degrees. So one wavelength would correspond to 360 degrees, half a wavelength, for example, to 180 degrees. Well, if we have a transmitted wave which is incident on a metal plate, it is reflected and can then be received by a receiver, as it is seen here. The transmitter and the receiver can also be within one instrument. Well, the length between the antenna and the reflector, let's call it small l. Then the travel length, that is forth and back, is 2l, the travel length. Well, the lengths, as I mentioned, sometimes are expressed in number of wavelengths. For example, is the length is just 12 millimeter. Then we have the travel length being 2 times 12 and 24 millimeter. So the travel length is 2 wavelengths. Number is 2 wavelengths. As I mentioned, sometimes it's also expressed in degrees. That would be 2 times 360 degrees. That is 720 degrees. Travel length 720 degrees. And that is then also called phase. The phase of the reflected wave at the input of the transmit-receive module is 720 degrees, and because it's some kind of delay, it's negative. It's minus 720 degrees delay. I remind you to the echo which you have in the nature, for example. Yeah, you have also the echo which is delayed when compared to the spoken sound which you did. Well, we should keep in mind the larger L, the more negative is the phase, and vice versa. Well, we have to look a little bit more. We have as we have seen here, the transmit receiver, the module with the antenna, with a forward radiated wave and reflected wave. And now we take in consideration that the antenna has only a limited angle in which it is irradiating. And we consider different distances of the metal wall, such as we had in our experiment. In a small distance, all the forward radiated wave is, when it is reflected, is captured by the antenna again, and then it gives a signal. Then if the distance is larger, we see that due to the reflections at the incident angle, but in the other direction at the metal wall, because of that, only a fraction of the radiated power is accepted by the receiver here again. And in the third case, we even see it's only in this simple representation, one line which is there. So that means the reflected signal which is received is smaller in all three from the one to the second to the third case. That is, becomes smaller when the plate is farther away. And furthermore, the travel length is becoming longer and longer. And the travel length also given in degrees. That means we can have a representation as it is here. We have this dot which we have here that gives the signal, represents the signal in the first situation. The length of this arrow represents the strength of the signal, and the angle which we have here, it's a negative angle, represents the phase of the received reflected signal. In the second case, the amplitude is smaller and the phase is more negative, because 2L is longer. And indeed, we have it here, approximately 90 degrees in this special case, more negative, and the amplitude is smaller. And even more in the third case, another approximately 90 degrees more negative, and the amplitude is smaller. So when we compare this, we see that we have a movement where along a circle, but the amplitude becomes smaller. That is just the spiral what we have seen in the experiment before. With this new knowledge, let us look through our experiment again. We see the metal plate beginning to move to increase the distance. We see that the spiral begins to move, and the distance increasing. The spiral moves in negative direction, that is clockwise. The amplitude becomes smaller and all tends to some central point where it ends then. Well, in addition to the metal plate, now let's see what happens when we do the same with the glass fiber reinforced plastic leaf spring, and we move it. Okay, we see we have a very similar behavior, also a spiral that tends to a constant value. In the course of the next videos, we will learn how an indication arises, an indication of a defect, and what we can conclude from the shape of this indication. So far for today, until next time. Meanwhile, if you want to know more about microwave testing, you may have a look at www.fitm.de. Goodbye.